Hello, everyone, and welcome back. We are now at part 2 of our Module 7 demonstration video. Just to recap, if you haven't seen part 1, highly recommended, must watch, right? So in part 1, we talked about ways to explore your data with an eye towards missingness and trying to look for patterns of missingness and visualize them either in tables or graphs. And we also talked about how to conduct a test called Little's MCAR test, which is a quick and dirty test to show whether or not the data can be considered missing completely at random. We were unlucky in this case, where we just left off. We ran Little's MCAR test, and it had a very small p-value, which means we really don't have any evidence to say that these data are missing completely at random. And that kind of makes sense because we know that this data set has quite a bit of missingness, and it's on two variables, education and income, in which people are less likely to respond for a lot of reasons that are probably not random, that are driven by sort of underlying processes or confounding variables. So now we're going to go a step deeper. So if you do Little's MCAR test and you find that your p-value is non-significant, you can sort of skip this next section. You could actually technically not do multiple imputation if you wanted. It wouldn't hurt anything to do multiple imputation if your data are MCAR, but really, if your data really are MCAR completely at random, then list-wise deletion is fine. You can ignore those cases. They don't have sort of evidence of systematic non-random missingness. But so the next step is, there's three levels. There's MCAR, there's MAR, missing at random, and then there's not missing at random. And so your job now as someone who's making an argument about your paper or your analysis is to really show as much as possible. If the data are not MCAR, you really want to hit the mark for MAR, missing at random. And what that means is you want to demonstrate to your audience that you have other variables in your data set that explain, that are related to, right, correlated with missingness, and that you include those variables in your model. So that's the key. I'll say it again. So if you're trying to prove MAR, missing at random, you need to show first that you have other variables in your data set that can predict missingness, that are correlated with missingness on particularly education and income, because those are the big variables where we see the most missingness happening. And two, you need to show that you've included those variables in your model when you do something like multiple imputation. And if you've done that, then you can make a pretty good case that you have met this missing at random assumption that it becomes so important if you can't hit the missing completely at random mark, which is actually very hard to do. So now I'm going to show you how to do this, how to sort of test for this. And to do this, we need to actually do a little bit of data management. So we need to create a series of indicator variables that tell us which people are missing the education variable and which people are missing the income variable. And so this is what we're going to do here. We're going to create two new variables, educat miss and inc miss. And those are going to be binary variables, and they're equal to 1 if the participant is missing on that measure and 0 if not. So I'm actually going to create a brand new data set. This is an advantage of R, right? You can just copy the existing data set and create a couple new variables. So I'm going to call this thing missing. I'm going to start with the Oregon data set, my original, and then I'm going to use the mutate function. So I'm going to create these new variables based on values of my existing variables. And then I'm going to rely on this case when function that we first learned about. I believe it was last week when we talked about logistic regression. So in logistic regression, we created a binary variable using case when. We're going to do something similar here. So my first variable here is called educat miss. And that is going to be equal to 1 right here when Oregon educat, so the educat variable in the original Oregon data set, is equal to missing. And the way I do this is I use this is.na function. So basically when this thing is true, right, when education is missing, that's what that statement means, this new variable is going to be equal to 1. Otherwise, that's what true means. All else, it's going to be equal to 0. So this is going to set up a binary variable that's equal to 1 when that variable is missing and 0 otherwise. And you can take this format and you can just change the name of these variables and the name of the data set. And you can do the same thing with your data. So then I'm going to create another variable called income miss. And that's going to be equal to missing when the original income variable is missing with this is.na function. So that's going to be equal to 1. And otherwise, it's going to be equal to 0. So this is, again, the case when function from the dplyr package, very useful. And it's going to allow us to create these missing variable indicators. So I run that, and here's my new data frame, missing. So let's look at that. So I'm going to open this up and go over here to the end. So here are my new variables, educat miss and inc miss. So a reminder, if these things are equal to 0, it means I have an observation. If they're equal to 1, it means I have a missing. So here, educat miss, 0, 0, 0. That looks right because the first 3 people in my data set reported their highest level of education, 12, 16, and 12. My first NA is right here, the 4th person, and the 4th person is equal to 1. So that's right. 5th person equal to 1. Good. And so on and so forth. I can check this pattern and make sure it makes sense. Same thing with income. My first missing on income is in row 7. 1, 2, 3. Oh no, it's actually not 7. It's further down. It's this one right here. So 1, 2, 3, 4, 5, 6. Oh, it is 7. Okay, so 1, 2, 3, 4, 5, 6, 7. There we go. So I'm just sort of spot checking to make sure this looks right. It's always a good idea with your code to make sure all your missings are lining up. Now notice I'm not coding missing both, although you could code that if you wanted to. I'm just trying to understand what is related to missing on income, what is related to missing on education. Okay. All right, so that's my new data set. We'll go ahead and describe this again using the describe function. And the most useful part of that are the last 2 variables here. These are my new variables. And the mean here should be about the proportion of observations that are missing. So here, the mean of educat miss is 0.25. So that means since it's only coded as 1 and 0, it means that about 25% of the observations are missing. That adds up with what I saw up above when I summarized. And inc miss is 0.14. And that also adds up with what I saw above. It's about 14%. Okay, so now I actually can use these indicators in logistic regression models as outcomes. So I'm actually predicting missingness on a given variable, which is really interesting, right? So I'm actually trying to predict what factors are associated with somebody not responding to education. I'm not predicting their education, right? I'm predicting whether or not they actually answered education. And that's what it means to investigate these missing variable mechanisms. And so here we learned about logistic regression last week. So I'm going to call this logistic 1. It's a GLM, generalized linear model, with a binomial from the binomial family. And my outcome here is educat miss, and I'm just going to put every other variable I have in this data set in there to see if any of these other variables predict missingness on education. And sure enough, a couple do, right? So my outcome actually predicts missingness on education. And I could do the sort of odds ratio transformation and try to interpret this, but for this, you can just kind of keep it simple. So a positive value here, remember, these are logits, these are log odds. So a positive value here means if somebody has a higher score on that variable, they're more likely to be missing education. So here, somebody who feels closer to their community is also going to be more likely to not report their education. I don't know why that is. And I actually, for our purposes here, I don't need to know why. I don't need to explore sort of the causal reasoning behind it. I just need to know there's a variable in my data set that predicts missingness on education. So that's good. The only other variable is health problems. People with diagnosed health problems appear to be slightly less likely to be missing their education, although that's only significant at 0.1. So at least I have one, right? This community variable is at least one variable that's associated with missingness on education. Now I'm going to do the same thing for income. All right, so instead of educat miss, I'm going to put in my inc miss or income. And here we get a bunch of variables. So this is good. I can make a really strong case that I have a lot of variables that are related to missingness of income. First of all, concern for education and public health, that's negative. So that means if you have more concern for those issues, you're less likely to be missing income. Concern for the environment is positive. So more concern, more likely to be missing on income. And male respondents are less likely to be missing their income. And people with health problems also less likely. Again, the actual interpretation does not matter in this case. Normally we would want to interpret that, maybe visualize it, wrap our head around it. All we need to show is that we do have variables in this data set that predict missingness, because that gets us one step closer to being able to say, we think these data are missing at random after we include all these other variables in the model, which is the key behind the MAR assumption. Okay, so I think that seems to be pretty good. I think we have some variables that can actually explain missingness. And so I think we can go ahead and proceed with multiple imputation. And so here we are with multiple imputation. This should be 5 data sets instead of 20. I adjusted this example a little bit. And so to do multiple imputation, we are going to use the MICE package. MICE, great name for a package, stands for multiple imputation via chained equations. The specifics of that are not as helpful right now. We don't have to go into it. This week's reading by Paul Allison has some really nice details about the different kinds of multiple imputation and why they're useful. Just a refresher from the lecture. Multiple imputation basically means take one data set and impute a bunch of possible values for the variables that are missing. So try some values and then repeat and then repeat and repeat many, many times. You could do it 5 times, 10 times, 20 times. And basically you are trying different combinations of plausible values, and then you're averaging those plausible values over time. Not unlike this concept of bootstrapping, right? Which is a resampling approach. Multiple imputation is not a resampling approach per se. You're using the same observations each time, but you are imputing slightly different plausible values for those observations that are missing. So the command for doing this is actually really straightforward in R. Once you've loaded in the mice package, the command is just mice. And this thing produces a model. So we want to give it a name. So I'm going to call this imputed data. So I'm going to do multiple imputation. I'm going to do 5 iterations. So this is low. We're doing this because it takes a little bit of time. I would recommend as many as 20, maybe even as many as 50 if you have time, all the way to 100. There's nothing wrong with doing more. Doing more imputations will not bias your results. So if you can do 100, I would do 100. So you would just change this to m equals 100. Max it. So that this particular process we're using, predictive mean matching, uses an iterative process. So 5 is fine. You can leave that at 5. Method, this is sort of the default. It's called predictive mean matching. It's fairly similar to what we do in Stata. It's a well-recognized approach. And then seed. This is a random seed. We talked about this when we did bootstrapping. So both of these approaches use what's called a random number generator to get things started. And so if you want to get the exact same results, you have to specify the same seed every time. And so I just put the zip code of VCU. This can be literally any number. It can be 1, it could be 1,000, it could be 999, whatever you want. And then we're going to get a summary of that imputed data. So this is all it is. It's kind of cool. And it shows you as it's, so here we have iteration 1. So it basically does this whole thing 5 times because we asked for 5 iterations. But so here, here is the first approach. So here are 5 copies of the data set, and then a second approach, 5 copies of the data set, and so on and so on and so on. And then we get our matrix of predictors that are included in each of them, and our imputation methods. So what we're doing is pretty straightforward. We are not doing separate imputation models for each variable. We're imputing them all at once. But if these were different, for example, you may want to impute a different value for male. You may want to impute it as a factor variable, although there was very little missingness on male. The 2 that we're really interested in are income and education, and those are both continuous. And so this approach works just great for continuous variables. But this is a hugely flexible package with a lot of different options. So just to share that with you. Okay, so then we can rerun our regression model with our 5 imputed data sets, and then it's going to automatically pool the results. So it's going to run it 5 times and sort of take the average automatically. And the command to do that is using this with command. So linear model 2, this is our imputed model, is going to be with the imputed data, our imputed data sets, and then a comma. And then we just specify our linear model. So this is the same linear model we ran at the beginning. The only thing we didn't include is the data statement. So data equals. We don't need that part because we've already told R that we're using imputed data. So it's using a special kind of process for this. And it runs. It's amazing how fast it runs. So here's linear model 2. And then we're going to get a summary of this. But first, since this is imputed data, we need to pool our results. So we need to use that pool command to sort of pull together and average all of our results. So we run that and we get our results. I wonder if I can make this a little bit wider. Let me try rerunning this. It may, there we go. Sometimes I use that bigger screen, so it's harder to fit it all in there. And there are our results. So here is our intercept. Here is our estimate for COM3. Here's our estimate for, again, concern for the environment was our outcome. EPHT, here's male, health problem, income, and education. And this is a complete data analysis. So all 4,508 people are included in this analysis because I have imputed all of these values, which is really, really cool. We can compare this. So we can compare some of these estimates with the estimates of our linear model, and I'll do that. That's not. I'll show you the plot in a minute, but we can compare our results. So income and education are the 2 that we were most worried about. So income is 3.5 times 10 to the negative 7th, and not significant. Up here it is 2.63 times 10 to the negative 7th. So it's a bit smaller. And not, again, statistically significant. Bummer. Thought we might get something, but we didn't. And education is -3 times 10 to the negative 3rd. And here it's -8 times 10 to the negative 4th. So interesting. These estimates are like off by as much as a factor of 10, which is pretty amazing. But still not statistically significant. But the nice part is, imagine if we only ran this model, right? A reviewer or someone could come back and say, this model only ran on a little over 2,800 people. What about the people that were left out, right? And that's a hole in your analysis, right? You can't really make an argument. You have to say, yeah, there was a lot of missing data. Whereas here you could say, look, when we compared this with our model where we imputed all the data and we imputed education and income, we did not see big differences in the statistical significance of either of these variables. And so it's a much stronger argument to show that even when you include everything and you use multiple imputation, that it doesn't make a big difference. So that's multiple imputation. Oh, and the last thing, so this is kind of a cool function. I think this is in NannyR maybe, NannyR, or it's in mice. I can't remember, but it's called strip plot. And this sort of just shows you where values are imputed. I'm going to do it for education. You can do the same thing for income. So strip plot on our imputed data. Cat is our predictor that we want to look at. We want to put what's called a random jitter on the data, and then this just controls the amount of the random jitter. I'll show you what that looks like in just a minute. Okay, so this is pretty cool. This shows you all of your imputations. Imputation 0 is your original data. And here are all the observations for education. So each one of these little circles, and notice they get pretty thick, right? These are values that were imputed. So you can get a sense of the data that were filled in and where those data were filled in. So any pink here are data that were imputed in our imputation model, which is pretty cool. So it gives you a sense of, so a lot of data were imputed here, sort of in the middle of the distribution, around like high school education, and it looks like a decent amount up here as well. Not so much, not as many observations were imputed at the low end. So it just gives you a sense of kind of where the imputation took place and whether or not it seems to look really strange. Here we have a nice blending of observed and imputed values. And so it's just a good demonstration to folks as to what you did. And that's something you could include in an appendix of a paper too, if you wanted to. All right, so just to summarize, we started up here with trying to understand the missing data mechanism. So we crossed our fingers and ran Little's MCAR test, and it was not significant. Or no, it was significant, it was highly significant. And so that means we couldn't say the data were MCAR. And so we created these predictors of missingness, educat miss and income miss. And we tried to find predictors that were associated with missingness in our data set. And we found a couple, which was great for each variable. And so we imputed our data based on all the variables in the data set using predictive mean matching. And we created 5 copies. And then we reran our model with our imputed data and compared our results. And then we looked at the quality of the imputations using the plot. So this puts together just kind of a comprehensive argument that you could make for how you handled missing data. I have an example in the lecture slides of how I wrote about something like this in a paper recently. It's a really great way to handle missing data. It works very well, and it's very flexible. You can do it for any kind of model. It doesn't just have to be a linear model. It could also be a t-test or an ANOVA using the same approach with, and then instead of LM, you could do AOV or any number of other commands. So this is a great approach to use. I hope you found it pretty straightforward and as useful as I do. So good luck and happy hunting with that missing data.